Welcome and thank you for attending our presentation, Mochii ISS National Laboratory Portable Spectroscopic Electron Microscope. I'm Chris Owen, CEO of VOXA, and I'm delighted to update you all on progress towards placing microscopic imaging and elemental analysis on ISS, and to share with you how you might be able to use Mochii onboard ISS for your own microgravity research. Team VOXA is a young company based out of Seattle, Washington. Our multidisciplinary team has significant experience in nanotech, electron optics, and software, and our products specialize in automation technologies for advanced imaging tools. Mochii ISS NL was created in partnership with NASA Johnson Space Center, aligning with the International Space Station's purpose to support science, technologies, and exploration with benefits to all humankind. I'll open with a reminder that we're surrounded by tiny, beautiful things. Here are a few examples. On the left, skin cancer cells colored in blue on pink columnar tissue structures imaged at the microscale. In the center, spinnerets of a spider extruding silk, colored purple. On the right, the fracture surface between a tooth and the darker titanium dental implant screw edge. The variability of nature and the technologies we build span many size ranges, including those that we can't see without the assistance of magnifying tools, in this case, the electron microscope. Knowledge of structure and composition are essential for technological progress, especially in space. While powerful analytical capabilities are available, on ISS many samples cannot be sent back to the lab, are extremely time-critical, or evolve or might be destroyed during transit. In 2013, Italian astronaut Luca Parmitano was performing a routine extravehicular activity outside the International Space Station when his helmet suddenly started flooding with water. After hurriedly bringing Luca into the airlock and back to safety, ISS crew members disassembled the suit and discovered a fan pump separator had been clogged with white particles of unknown origin, causing water from his backpack to flow into his suit. There was no known source for these particles, as the water in the suit was meant to be high purity. Root cause analyses were limited while the suit was still on station, as the composition and hence the origin of the particles was unknown. The suit was returned to Earth only 6 months later, after which the white particles were analyzed by scanning electron microscopy, or SEM, and identified as aluminum silicate. The root cause was determined to be contaminated water that had leached silicate compounds during storage, and a precipitation event on orbit caused the particles to accumulate in the plumbing and to malfunction. During this entire period, spacewalks were suspended and only resumed 17 months later, at the end of 2014, after the root cause was found and mitigated. If ISS had an SEM on board at the time, the root cause could have been identified and potentially mitigated in days rather than months, allowing a return to full ISS capabilities, including spacewalks, much earlier. At VOXA, we developed a new portable imager and spectrometer called Mochii for unprecedented in situ diagnostics in science. Mochii combines the best of both light and electron microscopes in the size of a coffee maker. In particular, it can provide nanostructure and material composition identification by way of SEM imaging and energy dispersive X-ray spectroscopy. Mochii's coffee maker footprint weighs less than 15 kilograms and consumes less than 100 watts of power. Due to its portability, it mitigates the need to send samples back, is remotely operable via tablets or phones, and fits in the overhead bin of an airplane. Mochii is just as at home on vehicles, whether on ocean vessels, oil rigs, or even space vehicles, as it is in the lab. We've tested in various environments ranging from undersea habitats, laboratories, and home kitchens, and we're now deploying onto the International Space Station as part of a NASA SBIR Phase 3 commercialization agreement. This will provide powerful new imaging and spectroscopy capabilities for broad use by the microgravity research community on ISS. To provide some background, here is how electron microscopes compare with light microscopes, which most everyone have had experience with. These tools are complementary, each with advantages and disadvantages. Light microscopes, left, have certain drawbacks such as limited resolution, contrast, and depth of focus. They can do depth sectioning due to their weak scattering. Electron microscopes, on the other hand, have advantages of higher resolution, contrast, and greater depth of focus, and due to strong scattering have excellent surface sensitivity. Both provide a form of spectroscopy. In the case of light, they are visible colors that we're all familiar with, and for electrons, the chemical composition is provided. A similar comparison can be made between X-ray spectrometers/imagers and electron microscopes. X-ray fluorescent systems come in portable and benchtop models providing elemental ID. XRF is portable in handheld models providing spectra from objects about the size of a dime. Micro-XRF can provide composition and images of objects as small as 10 microns, but is large and restricted to the laboratory. Due to the penetrating nature of X-rays, there is internal structure sensitivity. At the same time, due to scattering and air and working distance constraints, XRF is not traditionally good for identifying organics. On the other hand, despite providing exquisite resolution down to single-digit nanometers, electron microscopes are traditionally not portable, similar to micro-XRF. EMs are surface sensitive and due to the vacuum analysis environment are good for studying both organics and heavy elements. The electron microscope is a workhorse lab-based instrument used traditionally for materials development, forensics, and science in the laboratory. For those of you new to EM, the operating principle is similar to the triode vacuum tube. In a vacuum environment, a filament is heated and creates a stream of electrons that are accelerated by an anode typically biased to greater than 10 kilovolts. Next, focusing optics condense this beam of electrons down to a fine nanoscale size point, which is then rastered across a sample like in a CRT television. The interaction of the beam is collected onto an electron-sensitive detector, and also, as the beam interacts with the sample, X-rays fingerprinting the elements at the beam location are generated, and these may be detected forming a spectrum that can be used for chemical ID. Conventional electron microscopes are large and expensive, including so-called benchtop instruments, which typically weigh hundreds of pounds. A trained operator is required. More importantly, being a lab-based instrument, field samples must be sent back to lab for analysis, resulting in a long delay between sample gathering and subsequent analysis. Here's an example of how Mochii will be used on orbit. The application is started from the home screen in the iPad, and a Mochii is selected and connected to from the selector list. Clicking Explore gives access to the exploration portal, and the image comes into view. Navigation is accomplished through finger gestures from pinching, zooming, and panning. The image can be focused using a focus window, which allows focusing and astigmatism to tune up the image quality for maximum sharpness. A sharp image is now in view, and certain analyses can be done, such as measurement using the ruler tool, as well as energy dispersive X-ray spectroscopy. In this case, point spectroscopy of this small particle. The spectrum can be explored and peaks identified, and here we can see that there's good resolution of the light elements carbon, nitrogen, and oxygen, as well as heavier elements. The analysis is saved and also can be annotated using the notes feature, which is seen by all users on their iPads at the same time. The image is saved to the photo stream for future use. And from here we can exit the app and return back to the home screen. This part of the demonstration makes use of the spectrum imaging feature to analyze the components of a semiconductor device. The Area EDS tool is used to select an area to be analyzed for elemental composition ID. After starting the spectrum image, we select the color filters and proceed to detailed analysis. The acquisition continues to run as we set up peaks and tweak the filters. We can select specific elements to focus on as well as select filter windows for them. This high-definition acquisition is sped up by about 30x, and the spectrum color data can be seen filling in the image on the right as the acquisition proceeds. The peaks will change in intensity as the spectrum data comes in for different parts of the image. Once the acquisition is complete, the analysis can be saved to the photo stream, and we return to the image window to see how the spectrum map fits into the surrounding area. While Mochii is versatile and robust for use in the field, some sample preparation is required depending on the type of investigation. We have developed a field sample prep kit to replicate sample preparation tools from the lab. The kit includes typical tools such as tweezers, cutters, and manipulators, as well as carbon conductive tapes, all basic tools that are needed for SEM analyses out in the field. A further capability is the need for conductive coating certain samples whose insulative properties could impact EM imaging. To address this, we've built an integrated metal coating system that provides evaporative coating of heavy metals such as silver onto the sample. It's about the size of a small water bottle and piggybacks onto the vacuum system of Mochii to provide clean and even coating in the field. The next part of the presentation covers applications where Mochii can deliver new capabilities. The first is use on the International Space Station. Mochii is intended to be used for three main purposes aboard ISS. First, as a diagnostic device supporting crew and vehicle safety. Secondly, it will be made available for public use as a national laboratory facility for microgravity research and engineering. Third, it will serve as a platform for future mission research, including for Moon and Mars. After several years of detailed preparation, Mochii launched to the ISS on the NG-13 mission in February 2020, aboard the Cygnus space vehicle on top of a Northrop Grumman Antares rocket. This mission carries 7,500 pounds of supplies, food, and experiments, including Mochii, destined for the ISS. It was an amazing moment for our team to see a system we designed and built lift off the launch pad on a rocket and be propelled into low Earth orbit at 17,500 miles an hour. The Cygnus was captured a few days later after liftoff by flight engineer Drew Morgan and berthed with the ISS shortly after. On ISS, Mochii is planned to occupy the Japanese experiment module continuously. It is wirelessly controlled by iPad both from vehicle and ground by multiple simultaneous users. So far, the mechanical installation has been completed and the system is currently undergoing bring-up operations. After bring-up and verifications of function, Mochii ISS NL will be available for public use. For a highly sensitive instrument, mechanical integrity of the optical and electrical system is critical. The hardware was initially tested to engineering quality levels which provided numerous areas for improvement in the mechanical design for the next iteration. Mochii was subsequently vibe tested at a lower flight acceptance level that met the two-vehicle requirement for both SpaceX Dragon and Northrop Grumman Cygnus spacecraft, shown under the MEFL chart on the right. For this test, we calculated foam thicknesses for appropriate vibration attenuation using a NASA packaging simulator, and fabricated foam to be used for vibe testing. The measurements from the test closely matched the predictions from the simulator, as can be seen in the bottom right-hand curve for one vibe axis, showing that the target attenuation was reached. This test was successful, indicating that Mochii had a high probability of surviving the flight under these packaging and nominal vibration conditions. With numerous equipment on station and broadcasting satellites on orbit, there are many opportunities for interaction and interference. As an emitting piece of hardware, a major requirement for Mochii is EMI and EMC compliance in the radio emitting environment of low Earth orbit. We conducted multiple iterative tests to check for emissions and susceptibility, and found Mochii to have only minor exceedances which we were able to get exception compliance for. A further wireless and wired communications test was required to ensure that Mochii played well with ISS information technology systems, and could connect to both wired and wireless networks and connect to the ground routing through the Huntsville Operational Support Center. The ping times were found to be nominal, and we were able to demonstrate good control of the payload from the ground. A unique impact of operating in low Earth orbit is that our sensitive instrument moves at 17,500 miles per hour through Earth's magnetic field. This has a deleterious effect of potentially shifting the beam during critical analyses as the ISS orbits through Earth's magnetic field over 16 times a day. To combat this, our team consulted with the European Space Agency to obtain data on how the Earth's field varies spatially and evolves over time, and we designed passive magnetic shielding for Mochii to counteract the effect. We built a special Helmholtz coil apparatus called Monarch to subject the instrument to the orbital magnetic environment varying between 200 and 650 milligauss and verified function within required limits for all axes. The ISS is quite a noisy place, with many mechanical systems operating nonstop. To protect crew from excessive acoustic levels, Mochii needed to reduce its acoustic output significantly for operation on the ISS. We conducted iterative testing of Mochii's acoustic system, with several revisions evaluated at Johnson Space Center's acoustic laboratory to reduce Mochii's pumps and fans to a low acoustic noise level. This enabled the payload to operate within the ISS cabin environment continuously 24/7. In preparation for on-orbit use, our team operated Mochii in an underwater habitat under extreme hyperbaric conditions as we reported last year at M&M. The NEMO mission demonstrated successful use of Mochii in an analog mission environment, with crew members conducting research on samples collected from the underwater environment during extravehicular activities. Off-site collaborators were able to simultaneously analyze the samples from shore. See our late-breaking poster 6 from M&M 2019 for more details on this unique experience. Electron microscopy is often used for examination of semiconductors and semiconductor packaging, and for reverse engineering products. This example is a failure analysis investigation we helped a small business to conduct with Mochii. During the time of coronavirus, many engineers and researchers cannot get into their facilities to use larger laboratory machines regularly. Mochii's ability to go anywhere enables work to continue unimpeded, whether at home or at customer sites in the field. In this investigation, a rugged diode used in a high-speed rotary power generator kept failing, throwing off its Kovar cap under a few thousand Gs and damaging the apparatus spinning at very high RPMs. The investigation using Mochii's spectrum imaging feature indicated copper concentrated at the interface seam, resulting in weakness despite the strong housing components. Likely failure mode was fatigue exacerbated by a segregation of softer metals to the seam. ALH 84001 is a Martian meteorite fragment that was found in Antarctica and whose science was instrumental in the formation of the decades-long Mars rover program. The structures shown here, called carbonate inclusions, have analogs on Earth rocks with biogenic origin, formed through life processes of magnetotactic bacteria. In the late 1990s and early 2000s, there was a great deal of study and speculation about whether these billion-year-old structures in this meteorite could have formed naturally, or only with the assistance of bacteria. SEM and EDS were critical tools for these studies, and one such study from 1996 on a high-end field emission SEM is replicated here using Mochii. The composition of the inclusion as well as its boundary chemistry are well characterized. It's further seen that the modern detector of Mochii has greater sensitivity to light elements such as carbon and nitrogen, which are necessary to support life processes. There's great interest to station an SEM in Antarctica or remote outposts for geological institute studies and to help select geological samples for return. Crystallization is currently an area of active research on ISS. While crew member Don Pettit was on ISS, he experimented with crystallization of simple table salt from the ISS kitchen, which is kept in solution in small squirt bottles. This example shows a huge difference the microgravity environment makes in crystal growth, as seen in these two Mochii images taken at the same magnification. ISS table salt evaporated in Earth gravity, on the left, produces small merged, sharply faceted polycrystals, just micrometers in size. The same solution in microgravity, on the right, produced massive rounded crystals called Hopper cubes that range from hundreds of micrometers to several millimeters. Crystals typically nucleate from small energy perturbations around impurities, growing into crystals from those centers. In the case of Earth gravity, nucleation happens often and in parallel due to contact with the container. On the other hand, in microgravity, the energy perturbations are small, and the impurities are pushed to the outside of the solution, as seen on the surfaces of the crystals in this image, limiting nucleation and allowing fewer large crystals to form. Mochii can help visualize these types of changes in crystalline materials on-site immediately after fabrication. In fieldwork, impacts to the body from the environment can range from mild to severe. On the moon, for example, dust is extremely prevalent due to the electrostatic charge, which causes it to cling to fabrics and equipment, which then makes it onto the vehicle after EVA. At NASA Johnson Space Center, health researchers are studying inhalation of simulated lunar dust particles and its effect on the body. The researchers found that not only does dust naturally find its way into the lungs, some amount gets swallowed and makes its way into the gut. These are images of dissected rat intestine, which shows that grains of fine simulated lunar regolith dust, of sizes on the order of micrometers to tens of micrometers, embeds itself into the stomach lining. The composition is distinct, with the larger particles embedding into the convolutions of the intestine, while the finer dust also attaches to the smooth portions. These particles can irritate the linings of tissues and cause deleterious health effects over time. This type of knowledge has impacted the understanding of crew health during exploration and also can aid first responders as well as hazardous fieldwork situations. I hope you've enjoyed this presentation. In closing, VOXA is very excited to serve new analytical needs for both users on the ISS and in the field. Come visit us at projectvoxa.com, and we look forward to conversations with all of you. Thanks very much for listening.